Hello there folks. So we are about to start a new topic of normal distribution, which is the one where you get the nice bell curve going on. There's a distinctive thing about a normal distribution, which is true for so many things in life that you might want to measure from different populations of different sorts of scores or heights or whatever, is that you will very often get this situation where the mean and the mode and the median all end up the same, and everything is distributed either side of the curve totally symmetrically. And this happens time and time again, as long as one thing's true, that you've got this element of randomness in what's going on. And there are different areas where this might suddenly be taken away, this randomness. One is, for years and years, my favourite sport was cricket, and cricketers, they judge how good they are by their average, and in batting they would always talk about their average. When they're doing that, it would be specifically the mean, because the mean's always going to give you the highest score in batting, and the reason for that is every single batsman, however good or bad, will have a mode of 0, and that's because it's the only score that they always have. Because you always start on 0, you've got a chance of being out on 0 every time, so it skews everything heavily towards 0, so your bell curve wouldn't look nice at all there. I'll give you another example in a moment. Just by the way, there's no biscuits today. I've taken a little branch out towards something a little spicier, going with a little Bombay mix. I advise that, although not if you've got any peanut allergies in the house, which I do have, but I will sanitize everything properly before my daughter gets home, I assure you. Okay, moving on. Right, normal distribution then is the pattern into which our data should fall if it's been randomly collected and we haven't disturbed the randomness in some way. So what does it look like? It basically looks like a bell curve that I'm sure you've seen before. Yeah, that should always be getting closer. We have asymptotes to the left and to the right. It should be symmetrical, so that's an important thing. So if we all write all of this down, it'd be a great idea. So it's going to be symmetrical. What's going to be in the middle is the mean. Now, to give you a real idea of, and the mean we normally call x bar, don't we? Give you an idea of what this means and the normalness and where that comes in. There's a cracking story that I'm going to nick off Eddie Wu now, that's on his YouTube channel, where he talks about something that happened with a mathematician buying bread in, he's not sure whether it was in Spain or France, but he seems to be pretty sure it's happened. So it may be one of those apocryphal stories that didn't really, but let's go with it and pretend it did, whatever, because it's a cracking story. And the thing behind this is he always used to buy his bread from the same guy, and the bread that he was buying was sort of labelled as being a kilo in terms of weight, so it's a 1 kilo loaf of bread. And he got to the feeling that maybe didn't seem to be quite a kilo as far as he thought. So being a mathematician and small-minded in a certain broad-minded kind of a way, he started measuring his loaves of bread and recording it. And being a mathematician, once again, once he had recorded this, he thought he would see what it looked like in terms of its distribution. And he got a beautiful normal distribution like this. Only his mean, mode and median line, that was going down the middle, turned out not to be at 1 kilo. It was at 900 grams, just about. So he thought, right, here I go, I've got the evidence I need. And so he went public with it, which he could have just talked to the baker, really, I would have thought, but he didn't. He went to the local paper instead. Or did he take him to court? You see, I'm not totally sure. I think he took him to... Anyway, it ended up, so the poor old baker was named and shamed. And as a result, when the mathematician started going, he didn't change bakers, he still went to the same baker, I would have thought if I was a baker, I'd told him to sling his hook, but apparently he didn't. Apparently he carried on going. And his loaves did get that little bit heavier. And being a mathematician, he wanted to see what it looked like in comparison before. And so he carried on keeping his data. And after a while, when he put it into a curve, he noticed he'd got something like this. Actually, I think that probably come down like that. He got something like this. And this was indeed at the point where his mean was around about the kilo mark. So everything was sort of happier. But why has this happened? And the reason it happened was, and I'm not sure exactly how this then came out, whether or not he spoke to the baker or whatever, or whether he just realised, or whether he then started watching what the baker was doing. But the reason he was getting it like this was he was no longer getting random loaves, which is what the baker was giving him before. He was just giving him loaves taken from his tray labelled 1 kilo, and his average one was that bit under. He started thinking, oh, here comes that troublesome maths man again. I'm going to give him one of my heaviest loaves so I don't get this problem in the future. So he was basically getting the heaviest loaf of the ones that he could still see there. So the baker wasn't doing anything different in terms of the loaves he was making. He was just giving the heavier ones to the baker. And what that did was it skewed the data. Okay, so we're not bothered about the skewed data. We're bothered about normal if the randomness is still there. So if all of that's true, we've got a few more things that we need to know about it. And so it's symmetrical. The mean equals the mode equals the median. We need to know that. But we also need to know a couple of other little things. Now I'm going to put in, and it doesn't matter what your distribution is, this is an interesting thing. Remember last year we spent a fair bit of time working out standard deviation. And standard deviation, what was standard deviation? It was a measure of spread, how condensed your data happened to be. And what's great in here, so I'm going to take the word mean off there so we've got a bit more space. So there's our mean. This point here is one standard deviation above the mean. So we can call standard deviation above the mean plus, and that's our symbol for, I say that's our symbol, let's have a better go at doing that Greek letter there. One standard deviation above the mean, and here is one standard deviation below the mean. And what we discover is that if we put a line down there, roughly, and it's very close to, 68% of the data lies within one standard deviation of the mean. So all of that area there is about 68%. Now if I was to go further and I was to go to 2 standard deviations of the mean, we always get a very similar, or not, another very constant proportion of our data. You can see here that this is going to be virtually all of it. So if I add in this bit as well, so this is the 68% plus that, that's going to get us 95, very close to 95% of our data. So the vast majority. But you'll notice that I've put a third one on here. So sorry, that is the mean take 2 standard deviations, and this is the mean plus 2 standard deviations just there. If we go that bit further to here, now that should look exactly the same as that, shouldn't it, if I've drawn it totally spot only, and I go down here, spot only, is that a word? Possibly. Right, you get virtually all of the data, but by virtually all, we're talking about 99.7%. So you've got to be either phenomenally good or phenomenally bad. If that is the end of it, it may not be good or bad, but certainly at one extreme end of the data. If you're more than 3 standard deviations from the mean, then that is definitely into outlier territory, isn't it? And do you remember we did things where we sometimes outliers are defined at different points depending on what you need. So this is 3 standard deviations from the mean will get you to that. Now we can use those facts to work out various things, and I'm going to give you one little example before giving you some questions to work on. Right, so jot down this question, and that you'll notice that there's 1 or 2 things about this which are familiar. So once you might want to pause it until you've jotted it down, and then this n here, no prizes for guessing that this stands for, this is telling you that we're talking about a normal distribution. So that tells you that we're dealing with a nice even curve. So let's do a nice even curve, something like that. This here is telling us our mean. So in this case it's 8. What's our problem about? Diameters of a rivet produced by a particular machine, x millimeters, is, so the diameter is going to be quite a small rivet, and it's on average they're going to be 8, but they're going to be varying a little bit, and that's what this is about. 0.2 squared is the variance. And if you look in your formula booklets, you'll see, if you had forgotten, that the variance is the standard deviation squared. Actually, sorry. Yes, it's the standard deviation squared, and the standard deviation, actually what it says in the booklet is the standard deviation is the square root of the variance. So the standard deviation is the 0.2 is the standard deviation, and all the questions we've got here are about is interpreting that. So you're asked the probability that x is going to be bigger than 8, so we are talking about all of that. Well, you've got half on one side, half on the other. Because we're dealing with not discrete but continuous data, because it's something being measured, you can assume you're never going to have something exactly on there. So the probability of it being bigger than 8 is the same as the probability of it being less than 8, which is 0.5. The same chance. Now, 7.8 and 8.2, what do we notice about 7.8 and 8.2? 8 take 0.2 is 7.8. 8 plus 0.2 is 8.2. And thinking back to when I was telling you about all those little things about how many standard deviations away from the mean we are, we know that if you're 1 standard deviation away from the mean, so you could call that x bar, sorry, we could call that x bar plus the standard deviation there, couldn't we? And x bar take the standard deviation there. We have, looking at that zone there, we know that that is always very, very close to 68%. So you can say that that is 0.68. And that is all there is to it for today, folks. Getting used to that terminology. Right, so today I'd like you to turn to page 40, and we're looking at exercise 3A. starting off with question 1, for which you need to think about. It's going to be asking you whether or not data is discrete or continuous. So remember, discrete things are things you can count, continuous things are things that you measure, and you could continuously measure them ever and ever more closely, so you can never say exactly what they are. So that's continuous and discrete. And then the others, if you have a crack at questions 3, 7, 8 and 9, as long as you can do all of those, we'll be in the right place to move on next week and do the next part. Alright folks, take care, goodbye.